Welcome to online lecture series in organic chemistry, and we are discussing about the reactivity of metal complexes. In this video we are going to discuss the inert and labile complexes. The complexes in which ligands are replaced rapidly by other ligands are called labile complexes, whereas those complexes in which ligand substitution does not occur or takes place very slowly are called as inert complexes. And the terms labile and inert are the kinetic terms and refer to the rate of reaction and should not be correlated with thermodynamic terms like unstable or stable. It means labile complexes may be thermodynamically unstable or stable. As an example, hexamine cobalt 3, it is unstable and inert, whereas tetracyanonickelate 2 ion, it is stable and labile, and this can be understood by this dissociation reaction. When hexamine cobalt 3 it is treated with dilute acid, then there is a dissociation of this NH3 and cobalt bond, and dissociation constant K, it is 10⁻²5. So greater the dissociation constant, lesser is the stability and dissociation constant, there is inverse proportion. It means this complex is unstable. Hexamine cobalt 3, it is unstable but it is inert, whereas the dissociation constant for the tetracyanonickelate 2 ion, it is 10⁻⁻22. So dissociation constant is very less, and therefore this constant is highly stable. So there is no any correlation with the inertness or lability and stability or instability of the complex. Now the next point is correlation between electronic configuration and lability or inertness of the complex. The Taube suggested a relationship between d electron configuration of metal and lability of complex, and according to Taube, the inner orbital complexes having one or more vacant d orbitals are labile. For example, hexacotitanium 3, it is labile because it is inner orbital complex containing vacant d orbitals. So titanium, its configuration is argon 3d2 4s2, its atomic number is 22. In this complex, oxidation state of titanium is +3. So in +3 state, its electronic configuration is argon 3d1. So there is one electron in d orbital, and it is a inner orbital complex with the hybridization d2sp3, and you can see here, so inner d orbitals, these are vacant, it contains vacant inner d orbitals, and therefore this complex is labile. Now this can be explained on the basis of its mechanism. Actually, mechanism of substitution reaction of inner orbital complex, it is explained by the formation of an unstable 7 coordinate intermediate or transition state, and the vacant inner d orbitals are required to accept the electron pair from new ligand for the formation of additional bond in 7 coordinate complex, and therefore inner orbital complexes with vacant d orbitals are labile. For example, this is the complex, metal is attached to 6 ligands, and it must contain vacant d orbitals to accommodate electronic pair donated by 7th ligand, and there is a formation of 7 coordinate transition state, and then there is a exchange of ligand will takes place. So this is the mechanism for the how ligand substitution occurs and how inner orbital complexes containing vacant d orbitals are labile. Now inner orbital complexes, according to Taube, inner orbital complexes with no any vacant d orbitals are inert. For example, hexaco-vanadium 2, it is inert because this complex is it contain or it does not contain any vacant d orbital and it is inert. For example, vanadium atomic number 23, its electronic configuration is argon 3d34s2. In this complex, oxidation state of vanadium is +2. In +2 oxidation state, its configuration is argon 3d3, and it is again inner orbital complex with hybridization d2sp3, and these are the inner d orbitals, and there is no any vacant inner d orbital. So any inner d orbital complex containing no any vacant d orbital, it is inert. Now this is about the Taube's concept towards lability and inertness of the complex. Now according to valence bond theory, if same metal ion forms both outer as well as inner orbital complex, then for that particular metal ion, outer orbital complex will be labile and inner orbital complex will be inert. For example, hexaco iron 2. So this complex is labile because this is the outer orbital complex. In this complex, oxidation state of iron is +2 and its configuration is 3d6, and this is the outer orbital complex, undergoes hybridization sp3d2. So outer d orbitals involved in the process of hybridization. So the ferrous ion, when forms outer orbital complex, then it becomes labile. The same ion, that is ferrous ion, when it forms the inner orbital complex, that becomes inert. Inner orbital complex will be inert. So for example, hexacyano ferrate 2 ion, in this complex oxidation state of iron is +2 and its configuration is argon 3d6, and this is the orbital diagram, or it undergoes d2sp3 hybridization. This is inner orbital complex, and inner orbital complex of the same ion, that is ferrous ion, it is inert. So this is according to valence bond theory. Remember, according to valence bond theory, if same metal ion forms both outer as well as inner orbital complex, then its outer orbital complex will be labile and inner orbital complex will be inert. Now summary of this point is, if any particular complex contain metal ion with configurations d0, d1, d2, d7, d8, d9 and d10, then its high spin as well as low spin complex, or outer orbital complex or inner orbital complex, both are labile. Whereas when metal ion has a configuration of d3, then its outer orbital complex and inner orbital complex will be inert, and when metal ion has a configuration d4, d5, d6, and such a metal ion when forms high spin or outer orbital complex, then it will be labile, and when it forms low spin complex or inner orbital complex, then it will be inert. So these three electronic configurations are very important: d4, d5, d6 of metal ion. Metal ion with d4, d5, d6 configuration forming outer orbital complex, they are labile, and d4, d5, d6 metal ions when forms inner orbital complexes or low spin complexes, then such a complexes will be inert. So this can be understood by example of certain complexes. When calcium forms complex with EDTA or titanium forms complex with chloride, the configurations will be d0 and such a complexes are labile. This is about the distribution of electrons. Then when configuration is d1 for Ti3+ and molybdenum +3, then these complexes are also labile. D2 complex of this vanadium 3 plus, it is also labile. When D4 high spin complex of chromium, that will be labile. Then D5 high spin complex of manganese and ferrous, it will be labile. And D6 high spin complex of iron, this will be labile. Similarly, D7 complex, it may be outer or inner orbital high spin. So D7 complex of cobalt, it will be labile. D8 nickel complex, it will be labile. D9 copper complex, it will be labile. And D10 gallium complex with oxalate ligand, it will be labile. So all these complexes are the labile complexes. It means any metal ion with electronic configuration D0, D1, D2, D7, D8, D9, D10, whichever may be the complex, high spin or low spin complexes are labile, whereas D4, D5, D6 with high spin complexes, they are labile. Now the inert examples of inert complexes, all the D3 complexes are inert complexes. For example, vanadium and chromium complex with D3 configuration, these are inert. And low spin D4 complexes, for example chromium complex with cyanide or manganese complex with cyanide as a ligand, these are the low spin complexes with D4 configuration, these are inert. Similarly, D5 low spin complexes of manganese and iron, these are also inert. And D6 low spin complexes of iron and cobalt, these are also inert. Remember, D3, all the D3 complexes are inert, and D4, D5, D6 low spin complexes are inert. So this is about the inert and labile complexes.